Welcome everyone. Today we're looking at something really exciting. It's still part of optical phenomena, so it's part of the section of work with photoelectric effect, but we're looking at spectra. Spectra is the plural of the word spectrum. All right, so have you ever thought about how do we know what elements our sun is made out of? So you'll read in textbooks, you'll see on the TV or on the internet that the sun is hydrogen and some helium and all sorts of things, but you go, how do they know? It's not like we could have traveled to the sun and taken a sample of the sun and then looked at it. Well, it's actually quite easy to know. It's all about spectrums, okay? So we have done the nature of light, we've looked at wave revision, we did the photoelectric effect, we spent some time on the photoelectric equation, we looked at how current can change, and now we're dealing with this last little bit, spectra. Our key words are this: a continuous emission spectrum, okay, very important. We're going to look at a line emission spectrum, they are different. We're going to look at an absorption spectrum. And so let's break down what we're looking at with spectra, okay? Number one, we get a continuous emission spectrum. And we're going to talk about what that is, and we're going to show you some pictures. Then you get line emission spectra. They're similar, but not quite. Then, of course, we're going to have to look at what an absorption spectrum is. And the line emission spectrum and an absorption spectrum are like the opposite of each other, basically. They're like the inverse of each other, which makes them quite nice. A continuous emission spectrum is something like this, where what we see all the colors of the rainbow, and they just melt into each other. So there's no distinctive line where we can go, okay, the green starts there. Some of you may be able to see it, okay? I know I struggle, but it's how I see color. I have a family member who is colorblind, fully colorblind, so he only sees parts of this, and some colors all just look the same, and we all see it differently. But this is the spectrum we see when we see a rainbow. Okay, so when we see a rainbow in the sky, this is what we see. And these are all the colors that white light is made up of. So the light around me that's shining on me in the studio is white light. If I put it through a prism, I can break it up into these, okay? But there's ways to do that. So an emission spectrum, and the important word here is emission, is when certain frequencies of the electromagnetic radiation are emitted, okay, due to an atom's electrons making a transition from a high energy state to a low energy state. And most of you are going, well, thank you for not speaking Greek. Emission means emit means give off, okay? When we look at the structure of an atom, the atom has electrons, which you know, and those electrons sit in certain energy levels. Sometimes we can give those electrons enough energy that they jump into another energy level, but they're not stable there, they don't like it. When they go back to where they should be, they give off the energy they took in, and that energy becomes light. Remember, light is a photon. Photons have energy. That can become frequency. When we have electrons moving with a certain energy, that means they give off a certain frequency of light, and we can see that as a color. The color of light is determined by the frequency of the light. A line emission spectrum for hydrogen looks like this, okay? And it always looks like this. So now if you look at this, you can see there's only 4 colors that we can see. That's why it's a line emission spectrum. The last one I showed you was continuous because it showed all the colors. The black are colors that aren't emitted, okay? And it always gives me this pattern. It will always give me light, 410, 438, 492, and 663. You don't need to know those values, okay? You just need to recognize that you get the same pattern, and it's unique for hydrogen. Every element has its own unique pattern. And in fact, when they create these patterns from light from the sun, this is what they get when they look at the light coming from the sun. So that's how they know it's made out of hydrogen and other things, okay? But this is unique. The atomic absorption spectrum, now emission means give off. Absorption means take in. So now the difference is when certain frequencies of radiation that pass through a cold gas are absorbed. So this time, instead of going, I'm taking this and then I'm going to give it back to you and you can have that light, this time the atoms go, I'm going to let all the light pass through me except certain ones. I'm going to keep those, okay? And for hydrogen, if you look very carefully, can you see there's also only 4? And when I put those two patterns next to each other, that is the line that's emitted in a line emission, and that one, and that one, and that one. It's the opposite. So in the line emission, those are the ones that were given off. Now in the absorption, they're the ones that are taken in. How we create these spectrums is the difference. So how do we get them to give us these patterns? That's the difference. It's how we make them that determines what they look like. Just quickly to remind you, when you have electrons, okay, when they look like this, that's in their energy state. That's their lowest energy state. If an electron jumps, so there's another energy level over here with nitrogen, which has nothing in it. But this electron can be given energy and then it jumps. It becomes excited, but it can't stay there, okay? When it then goes back to where it should be, the energy that's given off is seen as light. So it's the transition between the energy levels. The more complicated the atom, the more lines we'll see. The more colors we'll see in an emission spectrum, the more black lines we see in the absorption spectrum. But it's all about this electron structure, okay? So, lots to think about. I know it sounds like chemistry. This is a bit of, this section goes into both, but it'll be asked in your physics paper. Think about what we've done. We're going to look at it in a little more detail in the next section. So take a short break. Well, we're going to take a short break, and we'll see you in a couple of minutes. Welcome back, everyone. We introduced the whole concept of spectra just now. So now we need to talk about how we practically get the spectra and what we use it for, basically. So let's discuss in a little bit more detail emission spectra. Now, the way we create an emission spectra is we need a hot gas. To get a hot gas, we need a discharge tube. This is very similar to neon lights, okay? So if you've got lights in your classroom, probably not at home because we use a lot of LEDs now, but those lights that have got long tubes, okay? Those are discharge tubes. And what happens is by putting a current so we've got a cathode and anode, so we allow current to move, and the electrons move from one side to the other, okay? And in fact, the electrons go towards the anode. That's what they do. By moving those electrons, we're giving energy to this gas, and we're exciting the electrons in there, okay? This is giving them electrical energy. That excitement causes the gas to glow. It causes the gas to give off light. Now, it's not always white light. So most lights we use in everyday life is white light. But if you've looked at neon signs, those signs they use at night, they flash different colors, or you've seen blue and orange and red and all those colors, they are different colors because of the gas that's inside the light, okay? That's where neon comes from. Neon, when it's put into a light, gives us a nice blue color. Okay, that's why they called neon lights, because they used neon gas originally. But this discharge tube allows this gas to give off light. So we're excited, we get it excited, it heats it up, and it gives off light. That's a discharge tube. Now, if we take this, so here's just an example of how we get it. This is the discharge tube that has got hydrogen in it, okay? We've put a light source, we've put a source, electrical source on either side of it. It's excited it, it's heated it up, and now we just have this whole spectrum like this, all this light everywhere. We need to narrow that down a little bit. So we use what is called a diffraction grating. It's a very, 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 very fine slit. That's probably a little too big. You're talking like if you had to take a needle and just put a line down a mirror. It's very thin, okay? That light is then put through a prism, but it's a 60-degree prism, very specific. That allows the light that's going through here to split up, okay? So at this point, we get what is called diffraction. The light splits up into the different frequencies that are actually making up the color we see. This isn't white light, okay? White light's made up of all the colors. This will have a specific color. That color is a mixture of all the colors that are being produced. This grating and the prism forces them to spread out because of their wavelengths. And then what's on this screen is what we see over there, which is a pattern I showed you earlier. Now, these values go to 1 decimal place. We're not worried about the actual wavelength. All right, you don't need to know that. But you can see that I've got 1, 2, 3, 4 again, just like we had earlier. Okay, so we've still only got 4. Hydrogen can only produce 4 lines. If I do this pattern and I get a different number of lines, it's not hydrogen, it's something else. Here we've got helium, and I know it's a little harder to see, but helium's got a line there, and 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 there. Helium's now got 1, 2, 3, 4, 5, 6, 7, 8 lines, and a couple of them are quite close together. Helium's the second element on the periodic table, so helium is actually a little more complicated, and it's more complicated because now it has 2 electrons, hydrogen only has 1. So there's very little its tiny little electron can do, whereas when I have 2 electrons, there's significantly more possibilities for the jumping between energy levels. Now look at iron. Iron's got lots of colors. Lots and lots and lots. Iron is a very complicated metal. Iron has significantly more electrons, that has more energy levels. That means there's far more combinations of how many electrons can jump, how far they can jump, where they go down. It just gets very complicated. The thing here is this. Each of these patterns is unique. So the light emission spectrum is like a fingerprint for an element. Scientists know if they get a specific pattern, it relates to a specific element. And it's how they can identify elements if they're not sure. They put it through a special piece of equipment that does this, converts it to a gas, puts it through a diffraction grating, and out comes this pattern. And then they can identify what element it is, and that's exactly what we did with the sun. Okay, so they know because they just don't do it as a hot one, they do an absorption spectrum. I'll show you that in a second, but that's how they know what color this needs to be, okay? Now, this is what happens. This is just an example. Here's my ground state, okay, of an electron. So we have electrons that's sitting here. This electron gains energy, okay, because it's heated, and it jumps, it gets to there. At this level, level 2, that's its ground state. That's where it's nice and calm, it's got the least amount of energy, it's all chilled, it's happy, okay? We give it lots of energy, so it's had way too much sugar for breakfast, and it jumps to level 6. Now, we know it can't stay there. Atoms and elements want to be in the lowest possible energy state. That's why they do everything that they do, because that's where they're happy. This electron now has some options, okay? So from there, it could jump all the way down to there. And if it does that, we're going to see purple light, violet light, okay? If it only jumped to that state, and now it goes down to here, we're going to see blue light. So the energy that's given off as it jumps down is the color we see. If it goes from here to here, we're going to see green. If it goes from here to here, we're going to see red. Now that's very general, okay? But it's a specific frequency which we can work out because we know that E equals HF. The E that we're talking about is the energy that's being given off there. So if I know how much energy is given off when it jumps, I can work out what frequency of light it is. So it's actually not as difficult as it sounded. When we get to absorption spectrums, this is different. This is done with a cold gas. So we have a source of white light. We then have the source of the element, the gas, which is cold. Okay, that's a cold gas. Not gold, cold. Maybe I should write it as gold, cold. That's what I'm wanting to write there. It's cold. Okay, so it's like going through a winter. Then it goes through the slit like we did before. It goes through a prism, but now this is the difference. Because it's gone through, because the white light, which is the source of the energy, goes through a cold gas, that cold gas absorbs the energy. So I'm going to keep some of these frequencies because it's nice. And then we get the black lines. So it's almost like a filter, okay? It absorbs some of the colors and the rest it goes, no, you can go, it's fine, I don't need you, all right? But like with the emission spectrums, this is unique. The more complicated the atom and the element, the more complicated this becomes, okay? And with the sun, they actually get it from this process. The sun is here, gives off light. When it gets to the Earth's atmosphere is actually like a cold gas for it. So that's why when they actually look at the sun, they create absorption spectrums, not emission spectrums, okay? because our atmosphere acts like a cold blanket almost, okay? And even though we don't think it actually does, it's much colder than the light that comes from the sun, okay? So that is the line absorption spectrum and the line emission spectrum for hydrogen. Watch. The black line for the absorption is the same place as the purple line for the emission. This black line is the same place as that. That's a dark blue. Not good with colors. Same as the light blue. Same as, that's an orangey red. They are the inverse of each other. These lines must be at the same place because they represent specific colors that have specific frequencies and specific wavelengths. Hydrogen can have only so many. That's never going to change. It is its fingerprint. It is its unique. It's like its DNA, okay? It's unique to hydrogen. This is our simplest one, though, okay? Because hydrogen is our simplest atom. You saw the iron one just now. The more complicated it becomes, the more atoms, the more energy levels, the more colors we either see or don't see, okay? So what do we need to remember here? The emission so we're looking at the spectra again, and we've got the emission, which of course can be continuous or a line spectrum, and then we have absorption, which is only a line one, and this line one and that one are the opposite of each other. Okay, and they are unique to each element, and we only get a continuous from pure white light. Welcome back. So we've done some theory and we've looked at some explanations, but of course we need to know how to use the information we know and do some calculations and see what sort of questions we can get asked, okay? So let's get going. Right, so they tell us, the simplified energy diagram show the possible electron transitions in an atom. So here we're going, that's my zero energy state. Then we've got energy level 1, 2, and 3. The higher the number, the more energy it has. And here they show it going from 3 to 2, and then S is 3 to 1. And in the other diagram, we've got P going from E1 to E2 and R going from E1 to E3. Then they say, using the letters P, Q, R, and S, identify the lines that correctly show transitions that will result in the atom giving off an emission spectrum. Emission means that energy needs to be given away. We only get an emission spectrum when the electrons go from a high energy level to a low energy level. So it's Q and S, okay? So Q and S are the ones that show the transitions. Why? Because the electrons are moving from a high energy level to a lower energy level and energy is emitted during this process. That's a nice question, it's a nice explanation. And how did I know? Because I looked at the direction of the arrows. Okay, that shows me the direction that the electrons are moving in. So these ones definitely have to show me which direction they're moving in. Okay, so the diagram below shows some transitions of electrons in an excited atom. Look at the difference from the last question. We have energy level 2, 3, and 4, but I now have given you values. As soon as you see values, you're going to have to do a calculation. That means we need to read the question carefully. Right. Do the transitions indicated in the diagram lead to absorption or emission spectra? Think about the question we just did. Okay. Here I'm showing it going from high to low, high to low. So which one are we doing? It has to be emission. Okay. Again, if they should ask you for the explanation, which they don't ask, please don't write explanations if they don't ask for it. If they did want an explanation, it's exactly what we did the last time. They're going from a high energy level to a low energy level, and they give off energy as they go. Now they say, calculate the frequency, so we want F, of a photon produced when an electron in an excited atom makes a transition from E4 to E2. Now, to calculate F, I need E, and I've got 2 here. What we need to recognize is the energy that it's going to have is the difference between those 2 energy levels. That's why they gave us the values. So that means this is going to be 2,044 times 10 to the minus 18 minus 1,635. Oopsie, that should be a times, not, I don't know what I was going to write there, but it wasn't a times sign. We're going to use our calculators because I know I can't do this in my head. So let's see, we've got 2.044 to the minus 18 minus 1.635, yep, times 10 to the minus 18, and I get exactly 4,09, which is actually quite nice. So this gives me 4,09 times 10 to the minus 19. I think that's what we saw. Yep, to the minus 19. I know it's small, but we've done lots of calculations and we know these values are small. But I am not finished because they wanted F. So we know that E equals HF. So this is 4,09 times 10 to the minus 19. H being Planck's constant, which we know, and if you don't, it's on your information sheet. 6,63 times 10 to the minus 34. So we want F on its own. So it's 4,09 times 10 to the minus 19 divided by 6,63 times 10 to the minus 34. Now, the nice thing is I still have that answer in my calculator, so I'm going to use that. Divided by 6.63 to the minus 34, and it's 6,17. at this point, I don't expect you to be able to tell me what color light that is. Not unless I give you some sort of table that asks you to identify it, all right? You are not expected to know the wavelength and frequency of different colors of light. It's just not in your curriculum. I can't tell you that. I would look it up in a book, because that's what books are for, okay? Now they say, what if it goes from E3 to E2? What we need to recognize here is it's a smaller jump, which means it must be a smaller frequency. We're going to do exactly the same thing. E is going to be E3 minus E2. So 1,937 times 10 to the minus 18 minus 1,635 times 10 to the minus 18. Don't put the units in. There we go. And we're going to put this on our calculators because it's important. Well, I can't do this in my head. 937 to the minus 18 minus 1.635 times 10 to the minus 18. Now I get 3,02. So that's okay, and we know that E equals HF, so this is 3,02 times 10 to the minus 19, and we have 6,63 times 10 to the minus 34 times the frequency. So now we're going to have 3,02 times 10 to the minus 19 divided by 6,63 times 10 to the minus 34. And again, I still have that answer in my calculator, so I'm not going to have to type it in again. I'm going to divide by 2.63 to the minus 34, and I get 4,56. And it's a smaller frequency, which is what I expected because I had a smaller energy jump, okay? You've always got to say to yourself, does my answer make sense with the information I was given? Don't just leave your answers. It's important that you think about it. Don't go and redo it. That's not what I'm saying. I'm saying think about it. Did I get a smaller answer? Yes. Was there a smaller jump between the two? Yes. So I'm happy that they're in line with each other, okay? We are going to take a short break, and then after the break, we'll carry on with some more calculations. So I'll see you in a couple of minutes. Welcome back, everyone. We're going to do some more calculations. We're all very excited because we're using lots of scientific notation, but it's such a nice section. So let's get going. All right, here we go. And it'll be on the next page. A simplified diagram of an apparatus experiment to investigate the photoelectric effect is shown below. Light of fixed frequency is incident. That means it just falls on it. On the cathode of a photoelectric tube. During the experiment, the ammeter registers the photocurrent. Don't worry about that term. They just saying a photocurrent because we have photons hitting it. They mean current. It's a normal current. There's nothing different to what we've done in electricity. So there's the setup. Okay, so here's the plate that's the discharge tube, okay, that we put the light on. The light hits the tube, the electrons then move to the other side, and because it moves, it allows a current to move, okay? Define the term photoelectric effect. The photoelectric effect is the ejection of an electron from the surface of a metal when light of sufficient energy is incident on it. Okay, so what am I looking for? It's the ejection, I'm not going to write it all out, of an electron, first of all, from, in fact, I am ending up writing it out, but that's okay, the surface of a metal when light of sufficient energy is incident on the metal. Now, straight away, because they've asked about the photoelectric effect, I pretty much know what the question's going to be on. Okay, it's going to be on the photoelectric effect. The intensity of the light is now increased. Intensity means that it's been made brighter. Then they say, how will this change affect the reading on the ammeter? In other words, what they're asking you is, if I have brighter light on my metal, is the current going to get bigger, smaller, or stay the same? Now, I've changed the intensity. I have to change the current. But I've made it brighter. When I increase the brightness, I always increase the current. So how will this affect the reading on the ammeter? The reading will increase. Now we've got to explain that. So we need to remember that the brightness of light is determined by the number of photons. So the brighter the light, the more photons are hitting the metal. And if there are more photons, more electrons can be ejected, right? So, brighter light has more photons. Okay? If more photons hit the metal, a greater number of electrons will be ejected before the current will increase. Just increase. The current will increase. Okay? Lots of explanations in these type of questions, okay? If you look at my explanations, I do them in point form. Try not to write a paragraph, because sometimes when you write paragraphs, you write yourself into little circles, and then your examiner looks and goes, I don't know what you're saying. And that's a problem, okay? When the frequency of the incident light, so this is the frequency of light we're using, so that's F. The maximum kinetic energy of the photoelectrons is 2,9. So that's EK max. They want to know the maximum wavelength of the incident light that will emit an electron from the cathode. You've got to read this carefully. Maximum wavelength. We talk about a minimum frequency. Frequency and wavelength are the inverse of each other. So if we have a high frequency, we have a small wavelength. If we have a small frequency, we have a big wavelength. This is asking you for your threshold wavelength. And now you're all going, but we haven't worked with threshold wavelength. Don't worry, that's why we look at the equations, okay? Because I've got E max there, I know I'm going to have to use E equals work function plus EK max. We know, so I'm just going to, that E equals HF, and we know that that's also HC over lambda. So when I look at this, I'm going to go, well, I know the frequency of this incident light, so this is going to be HF. We want the maximum wavelength, so instead of HWO, I'm going to put HC over wavelength plus EK max. You know, we've actually done the hard part. This is the science. Now it's substitution. So this means this is going to be 6,63 times 10 to the minus 34. My frequency is 5,9 times 10 to the 14. That's going to be equal to 6,63 times 10 to the minus 34 times 3 times 10 to the 8. Those are constants. They're on your information sheet. That's going to be divided by the wavelength. And they told me that this was 2,9 times 10 to the minus 19. And this just all looks horrible, but it's really not, okay? I'm just going to need to save some space here. So what I'm going to do on my calculator right now is I'm going to go 6,63 times 10 to the minus 34 times the 5,9 times 10 to the 14, and then I'm going to minus the 2,9, okay? Because I need to just get some space for us, because I need to show you what to do after that. So 6.63 to the minus 34 times 5.9 to the minus 14. Then I get that, and then I'm going to minus 2.9 to the minus 19. I'm going to keep all the decimals because I'm not finished with my calculation. So I've got 1,0117. Let's just check that I've got the right answer there. Yeah. Times 10 to the minus 19. Okay, and over the lambda. Now, to get your final answer, I'm just going to use a different color quickly. So those two are going to swap places on my calculator. Okay, so the nice thing is doing this, that answer is already in my calculator, so I don't have to worry too much about that. So here we go. I'm going to go 6.63 to the minus 34 times 3 to times 10 to the 8. I'm going to divide it by the last answer I had. No, never mind. Apparently I can't use my calculator either. We're just going to type it all in. 6.63 to the minus 34 times 3 times 10 to the minus to the 8. I'm now going to take that, divide by 1.0117 to the minus 19. And I get 1, we'll round that off to 2 decimal places, so 1,97. Times 10 to minus 6 meters. At this point, please don't change it to nanometers or micrometers or whatever, because if you do the conversion incorrectly, your final answer is incorrect. But if you do want to do the conversion, Because that's -6, that's micro. So this is the same as 1,97 micrometers. That's actually quite a big wave in terms of light, which means this threshold frequency for whatever this is very, very low. So it's easy to get electrons off this one. But they're not going to ask you to comment on the final answer that you get. They're just not. Okay. We've done a lot of stuff. We've worked lots of things. This is now learn work. You now need to practice. The more you do, the easier this becomes. We've come to the end of this lesson, so it's time to say goodbye, and I'll see you again next time.